In less than 2 weeks, a massive space object named Atlas, weighing 33 billion tons, will zoom past the Sun at incredible speed. It's moving 80 times faster than a speeding bullet. Here's what makes scientists nervous. Its travel route lines up almost perfectly with where the planets orbit. Random comets shouldn't do this, which brings up a troubling thought. Is Atlas just a natural space rock, or could it be some kind of craft built to slow down near the Sun and stay in our solar system? When Atlas passes behind the Sun, we won't be able to see it. We'll only know what happens when it comes out the other side. The scary part is what we can't observe during the most critical time. Atlas is speeding toward the Sun at about 55 kilometers every second. Its route seems almost impossible by chance. Imagine a car merging perfectly into the correct highway lane. Most comets come diving in from steep, random angles. But Atlas moves almost flat through the area where planets travel, tilted only 5 degrees from what scientists call the ecliptic. Think of the ecliptic as an invisible plate where planets circle, like a coin spinning flat in the air. For a visitor from outside our solar system, this is extremely unusual. Objects arriving randomly should come from all different angles across the sky. Most would miss this flat planetary zone by a lot, like balls thrown from every direction. But Atlas's path nearly matches where the planets move, as if someone programmed it to blend in with local space traffic. It's like a driver who somehow knows all the road rules in a city they've never visited. Scientists who study planet movements ran computer simulations. They found that only a tiny percentage of objects from outside our solar system should arrive like this. The ecliptic is just a thin slice when you look at the whole sky. For a comet to come in within 5 degrees is like throwing a dart at a spinning Earth and hitting one specific street. It's technically possible, but extremely unlikely. The previous 2 visitors from outside our solar system, Oumuamua and Borisov, came from steep angles. Their routes cut sharply through our solar system, like planes flying way too high or low. Atlas is different. It moves backward compared to the planets, but stays nearly flat on that same plane. It's like swimming against the flow of water, but staying right at the surface. This alignment isn't just interesting, it changes what could happen at perihelion, which is the closest point to the Sun. When an object approaches along this flat path, it meets the Sun at a shallow angle. This gives more time for any maneuver using the Sun's gravity, like a skateboarder using a ramp to pick up extra speed. If someone were designing a spacecraft to use something called the Oberth effect, a technique to boost speed by firing engines near the Sun, this is exactly the path they'd pick. Atlas was found on July 1st, 2025 by a survey team in Chile. It's only the 3rd confirmed object we've spotted from outside our solar system. Its entry speed of over 200,000 kilometers per hour proves it's not tied to our Sun, clearly not a local resident. On October 29, 2025, it will reach its closest point at 1.36 astronomical units from the Sun. That's just inside where Mars orbits, like passing between 2 moving vehicles on a highway. Based on how orbits work, it should swing around the Sun and leave forever. But the strange way its path lines up with the ecliptic, combined with its extremely high speed, leaves one nagging question. Is this just cosmic luck, or does it show signs of planning? As we count down to perihelion, the situation becomes more important. If Atlas is natural, it's rare but explainable. If it's not, the path alone suggests careful planning that goes way beyond random chance. At perihelion, Atlas will be moving at almost 68 kilometers per second. That's more than twice as fast as the quickest spacecraft humans have ever launched, like a cosmic bullet. This is when the laws of space movement offer a special trick called the Oberth effect. Hermann Oberth first explained this in 1929. The idea is that firing a rocket engine works much better when you're already moving fast in a strong gravity field. Put simply, the same push from an engine does far more when you're moving faster, especially near something massive like the Sun. It's like hitting something hard instead of just tapping it. Here's the basic rule. The energy change from firing engines depends on how fast you're moving when you fire them. If a spacecraft uses its engines while moving slowly through deep space, it gets only a small boost, like pushing a parked car. But fire those same engines while zooming past the Sun at 68 kilometers per second, and the effect multiplies, like pushing a car that's already speeding. A change of just 1 kilometer per second at that speed dramatically alters where the object goes. The math is straightforward. Energy increases with speed squared. So firing engines at perihelion is like swinging a hammer with full strength, not just tapping gently. For Atlas to get captured by the sun, it would need to slow down, what engineers call a retrograde burn, right at the closest point. The goal would be losing enough speed to change from escaping our solar system to staying in orbit around the sun. It's like slamming the brakes on a speeding car to pull into a parking spot. Calculations show that to settle into a stable orbit at 1.36 astronomical units, the object would need to lose about 20 kilometers per second at perihelion. That's a huge requirement. Even with the best chemical or nuclear engines we know about, the fuel needed would equal roughly the object's own weight, like a car carrying its weight in gas. However, the Oberth effect is the only way such a maneuver could possibly work with any technology we understand. Natural comets do release jets of gas and dust that can slightly change their paths. But these forces are weak, random, and rarely helpful for changing orbits. They might change a comet's speed by a few meters per second, not tens of kilometers, the difference between a light breeze and a hurricane. A controlled, perfectly timed burn at perihelion would be obvious in the data. The resulting path change would be clear to astronomers tracking it after it passes the sun. The telltale sign would be a sudden, sharp drop in exit speed that can't be explained by normal gas release, like a car that suddenly slows down for no visible reason. That's why this perihelion window matters so much. If Atlas tried to slow down, the sun's gravity would amplify the effect, turning a modest push into a major change. The mechanics are clear, and the energy involved is enormous. What's left is watching for any sign that nature, or something else, has the ability and desire to use this opportunity. From mid-October through early November 2025, Atlas will disappear behind the sun from our view, like an actor leaving the stage at the play's most crucial moment. This isn't bad luck. It's the result of a fixed rule in astronomy that can't be changed, like a law of nature. When a target gets within about 30 degrees of the sun, all major ground telescopes must look away. It's like being unable to stare directly into a spotlight. Avoiding the sun isn't just about protecting sensitive equipment from blinding light. It's a built-in safety rule, like automatic brakes in a car. The blackout period from October 22nd to November 7th means that while Atlas races through perihelion, we can't take any direct pictures or measurements from Earth. Space telescopes face the same limits. Hubble and James Webb are programmed never to point within 50 to 85 degrees of the sun, eliminating any chance of a last-minute look. Even TESS, with its wide cameras, is blocked by safety rules, like having to close your eyes when light is too bright. The Parker Solar Probe and Solar Orbiter are both built to study the sun up close. They point at the sun and rarely risk turning away for other science. Their instruments are designed for plasma and magnetic fields, not faint objects at the edge of their view, like using a microscope to try seeing the moon. Mars orbiters, which are slightly better positioned, tried risky snapshots as Atlas grazed past in early October. But the object was 50,000 times dimmer than their usual targets. Initial images from ExoMars's Trace Gas Orbiter were dismissed by the ESA team as probably just noise, like trying to photograph a candle in a snowstorm. No confirmed sightings were announced. For now, all we have is absence, like trying to watch a movie with the screen off. For several weeks, any dramatic change, natural or not, could happen without us seeing it. When the object reappears near sunrise in November, astronomers will look for clues about what happened in the dark. Brightness should tell us about mass. For Atlas, that assumption is now being questioned, like finding out someone who looks heavy actually weighs almost nothing. Light measurements, compared against standard comet reflectivity, suggest the object weighs about 33 billion tons. That would make it one of the heaviest natural visitors we've seen recently. But when scientists checked the numbers after Atlas flew by Mars on October 3rd, they found nothing, like throwing a rock in a lake and seeing no ripples. At just 29 million kilometers away, an object that size should have slightly pushed Mars's orbit, or at least shown up as a small oddity in spacecraft navigation data. Instead, the Mars Reconnaissance Orbiter and ESA's Trace Gas Orbiter reported no measurable pull, like a massive truck driving past without making the ground shake. Deep Space Network tracking records showed nothing above normal background noise, like listening for a whisper in a quiet room and hearing nothing. This isn't just about missed signals. In 2014, when comet sightings spring passed much closer to Mars, it left a detectable mark on the planet's path. Even though it was smaller and lighter than Atlas should be, with Atlas having an estimated mass much larger, there's no effect at all, like a ghost that leaves no footprints. The difference hasn't been ignored. Space navigation teams double-checked their orbit calculations, searching for any unexplained drift in Mars's motion or spacecraft signal timing. The answer stays the same. No gravitational pull, no leftover effects, no evidence of a massive solid core, like a balloon that looks heavy but is full of air. Some suggest the mass is simply overestimated, that Atlas's brightness could be inflated by dust or an unusually shiny surface, like someone wearing bulky clothes that make them look bigger. Others point to the possibility of a hollow or very porous structure, a cosmic shell rather than solid rock, like a ping-pong ball instead of a bowling ball. The spin rate, measured from periodic brightness changes, suggests something spinning faster than a solid chunk that size should allow, like a top spinning too fast to be made of iron. For now, the numbers don't make sense. A bright, fast-spinning object with almost no gravity, an equation pointing to a hollow shell, whether made by nature or something else. Scientists tracking Atlas in mid-September recorded a cloud of gas extending 180,000 kilometers, an envelope around the nucleus bigger than the object itself, like a cloud the size of a small country. The main molecule in these measurements is hydrogen cyanide, being released at a rate of 4.5 times 10 to the power of 25 molecules per second. That's about 2 kilograms of HCN venting into space every second, like a constant leak of poisonous gas, though in the vacuum of space. This number stands out among known comets, but isn't impossible, like finding a very tall person, but not impossible. The huge size of the cloud and steady cyanide production suggest active outgassing driven by sunlight heating ancient ice. As Atlas gets closer to the inner solar system, jets of vapor and dust flow outward, shaped by radiation pressure and solar wind, forming an uneven halo that signals motion and activity. However, the chemistry is more than just interesting. It's the baseline for how a natural comet should look before perihelion, like a chemical fingerprint. The presence of HCN, along with traces of water and carbon monoxide, places Atlas in familiar solar system comet territory. The spectral patterns match those cataloged in previous interstellar visitors, though the proportions and intensities suggest a unique formation history, like a familiar recipe with slightly different ingredients. For now, the cloud's behavior supports a natural explanation, a volatile-rich, porous body shedding mass as it approaches the sun, like ice melting in heat. This baseline, measured before the critical solar encounter, will become the reference for judging any changes after perihelion. If the chemistry shifts or the cloud breaks apart in unexpected ways, those differences will stand out against the careful September records, like false notes in a symphony. A hollow shell racing toward the sun is more than a physics puzzle. It's a scenario that can be tested, like an experiment that can be proven or disproven. Imagine a structure built not to last, but to unfold. At perihelion, when sunlight and gravity are strongest, a fragile body could naturally break apart, scattering debris in random directions. But there's another possibility, one that scientists like Avi Loeb want to keep considering: intentional deployment, like a flower opening its petals at the right moment. If Atlas is designed, perihelion offers a unique opportunity for action. Instead of chaotic breakup, the shell could release smaller units, probes, or sensors, each with its own path, like dandelion seeds catching a gust of wind. In this case, the evidence would be concrete. After perihelion, astronomers would look for distinct, non-random trails spreading from the original path, like fireworks that explode in specific patterns. Some fragments accelerating or steering away from the sun, not just drifting. Patterns in the debris field, straight lines, sudden speed changes, or clusters moving as if controlled, would stand out against natural chaos. Loeb's Galileo project is preparing for exactly this test. His checklist is clear: track every outbound fragment, measure speeds, Compare against natural comet breakup models. If the data shows randomness, the design idea disappears. But if the sky reveals order, the implications are huge, like finding organized footprints instead of random tracks. The days after perihelion will decide which story the evidence supports. The ExoMars Trace Gas Orbiter, built to scan the Martian surface, was temporarily repurposed as Atlas passed Mars in early October, like using a microscope to try seeing stars. The instrument team turned their high-resolution camera from the planet to empty space, capturing a series of 5-second exposures, each pushed to the technical limit. The target was nearly 50,000 times fainter than anything the orbiter was designed to photograph, like trying to photograph a candle from miles away. Raw images showed little more than digital static. In most, the supposed comet couldn't be separated from background noise, like looking for a needle in a haystack of pixels. Processing software tuned for sharp Martian terrain struggled to pull out any reliable signal, like trying to use a coffee filter to sift sand. Analysts at the European Space Agency marked the preliminary images as likely noise, not confident enough to claim even a weak detection. The challenge wasn't just dimness. Mars orbiters send data back to Earth in tight windows, competing with planetary science priorities and data transmission bottlenecks. Each batch of images went through layers of calibration, compression, and review before reaching public archives, like a letter passing through many hands before reaching the recipient. With the object so close to the Sun from Earth's perspective, there was no way to verify these unclear images against ground-based observations. By the time any processed data becomes public, scheduled for late November, weeks will have passed since perihelion. In that gap, any sudden change in Atlas's path or structure could go unnoticed, like missing the most important moment of a movie because you left the room. For analysts, each unclear pixel is a reminder. The most critical moment might be hidden in noise, and the only clues could arrive too late to capture in real time. A body from interstellar space captured by our sun would rewrite planetary science, like discovering a new law of physics. For researchers, it would mean the first permanent sample of material from beyond our solar system, an object to study for generations, like having a piece of another world in our backyard. For defense planners, the scenario is less academic. Internal memos circulating at NASA and the U.S. Space Force during the blackout window outlined backup plans. If a designed object used a perihelion burn to lose speed, surveillance protocols would escalate, like increasing security when there's a potential threat. No agency has released public guidance or threat assessments. But the existence of those drafts, even in censored form, signals a shift in how such arrivals are thought about. A single headline about capture or probe deployment could trigger panic far beyond the scientific community, like fear that spreads faster than the news itself. However, despite all speculation, evidence remains king. To judge extraordinary claims, observers need a clear checklist. First, watch for a sudden change in exit speed, an abrupt drop visible in position measurements that can't be explained by normal comet outgassing. Next, look for organized debris, distinct trails or fragments accelerating in non-random directions, not the chaotic spray of natural breakup. Cross-reference with atmospheric anomaly records, especially UAP-type event reports synchronized to perihelion, like connecting dots in a puzzle. The data to watch is public, ground and space-based optical and radar observations, polarization studies, and citizen science measurement campaigns in the Southern Hemisphere. Archive channels from NASA, ESA, CNSA, and the Galileo project will release recovery images, trajectory solutions, and raw sensor data in November and December. The rule is falsifiability. If the exit path shows no sudden change, if fragments drift randomly, if no related anomalies appear, the story returns to nature. The test isn't what's possible, but what the data confirms, like a detective who needs evidence, not just theories. On October 29, 2025, Atlas will reach perihelion at 1.36 astronomical units from the Sun, a fact verified by both Atlas survey records and NASA trajectory data. Its near-ecliptic approach of 5 degrees is statistically rare for interstellar objects, as confirmed by orbit models, like winning the lottery, possible, but unlikely. While light measurements estimate a mass of 33 billion tons, The October 3rd Mars flyby produced no detectable gravitational effect, an inconsistency documented in ESA and NASA navigation records. Imaging gaps during the solar conjunction blackout are a matter of published telescope schedules, leaving a critical window unobserved, like having to close your eyes at the most important moment. So far, no classified defense advisories or market alerts have been released about the object's potential capture or artificial origin. Whether Atlas is a porous comet or something designed, only post-perihelion debris patterns and speed changes, expected in late November data sets, will offer answers, like waiting for crucial test results. For now, the evidence highlights both the limits of current observation and Atlas's extraordinary nature, like having almost all the pieces of a puzzle but still not being able to see the complete picture. Its next move remains a matter of record, not speculation, like watching a movie where the ending hasn't been written yet, but will be revealed in real time. The countdown continues, and in a few weeks, we'll know if we're witnessing the strangest comet in history, or something that will forever change our understanding of what's possible in the universe. The silence of space has never been so loud.